And hopefully the lecture before that we can review too. So far though, I like how this has been going. We've kind of been building on the topics and reviewing as we go, if you've noticed. If you didn't, well, we were. So I think you'll be prepared by the time we get it. Also, over here, I went ahead and posted your next homework assignments, which is due January 27th at midnight, right before. So you should have time to finish that. And yes?
So the test is going to be chapters 1 through 5?
Yep. Yep. Yeah. How come it's not giving me a scroll bar? Because it's doing the resolution projector thing. Swell. Yeah, well, you know where the announcement is. That's what it says. It will be covering chapters 1 through 5. That's what it says over here. This is to give you a heads up where we'll be heading after the test. You know, for all of you go-getters that start reading ahead. Okay. I think your free trial's about up. I don't remember if there's a day left or something. I think it's Monday. Anyway, point being, if you haven't purchased your online access code, you'll be trapped out and can't do anything, so you'll need to do that. Alrighty, let's do some questions. A way to review and continue on, and use your clickers. So, let's see. While you're getting them out and looking at that, some more administrative stuff. I learned, for a few of you that attempted to contact me through WebAssign, and before I continue on, it's faster and cleaner if you just send it right to my email listed in the syllabus. I've now figured out where the button is so I can forward such messages to my email, so I'll know. But I also learned, duh, you guys can too. There's notifications. If on your student view, it's in the top right, under notifications, you can set up certain things like it'll give you assignment reminders. Like, oh, you know, 30 hours before an assignment's due, it'll send you an email. Or if I change a due date, it'll send you an email or an announcement. That way you don't have to keep going back and check. You guys probably already knew this, and it makes sense, but I didn't tell anybody unless you weren't aware. Notifications, settings, you can adjust those however you would like to help yourself out. Also, I know Kate, remember Kate, you were one of them. I found the messages. They're not under messages. They're under Ask My Teacher. Under that assignment, there was an Ask My Teacher button. I went back into that assignment, clicked on Ask My Teacher. Ah, there was yours and my reply. I couldn't find them. So it's still there. Or anybody else that did that. Yeah, that's where it was, yeah. There's an Ask My Teacher button, and then there's a private messages, and then there's my email, and then that's why I'm just trying to keep it all in one place. If you just send it my email, it's less hassle, and we might not miss it. I've since put little things on there that if somebody does those in WebAssign, it forwards to my email, so I'll see it sooner. And, yep, sorry if I mispronounce it, Ryu, wanted to just add the class she here. Actually, I apologize. I don't even know if that's a he or she. R-U-I, first name? Well, then never mind. Back to this question, now that you've had time to think about it. Let's open polling. And you can start responding. Channel 44. Oh, yeah. You got it, huh? All right, let's see. Channel 44 it is. All right. So say you like answer A. You just hit A. So I have to hit enter. because I'm on the channel thing. Okay, channel change, 44, that's good. Find channels. It's searching for that thingy. Come on, baby. So meanwhile, back at the ranch, how you doing?
Good.
Good. Good. Let's just hit A and see what happens. How can it not find it? Yeah, I'm still on 44. What's its problem? Scarier. Channel changed. Okay. A. All right, if you don't like A, hit something else. All right. We're getting responses. So you're lying on the sand, and the fly's buzzing above you. This is one of those relative motion ones. There's a slight breeze blowing at 2 meters per second. So the key here is the last sentence. In order for the fly to land on you, it should hover over you while flying how fast? So if the wind is going 2 meters per second, how fast does he need to go to hover? And this is where you have to think, and I'll help you. Hover means what in terms of physics and his motion? Yes, I heard that. Who said that? That's right. It's in equilibrium, which means the net force is 0, which means he's not accelerating. You know, hover means he's kind of standing still. But there must be two things going on to be in that equilibrium. So I'll close the polling, see what you guys thought. Most overwhelming response of A. There we go. You're right. Does that make sense for those that didn't? If the wind's blowing this way at 2 meters per second, then you need to be flying 2 meters per second that way to counter it, to have a net force of 0. There's some force trying to propel you. You need another force trying to propel you opposite. All right. This one should be easier, I hope. Just want to make sure you're getting it. It's open. Your speedometer tells you what? This is basically, do you know what the difference between speed, instantaneous average, acceleration? What's that speedometer telling you? You look at it all the time probably. Let's relate it to physics and make sure you got it straight. While you're thinking, hi camera guy, is this high enough? You can hear me? Great. All right, we had 40-some responses last time. I know there's over 70 people registered. So what does that mean for, I assume, a big chunk here? Some people probably aren't here, but are you just opting not to participate or buy one of these? Who here doesn't have a clicker? Only one. Oh, okay. I guess I could count you all up, but it seems like there's more than 45 of you. Channel 44. We got 48 responses. Going once, going twice, one more. Oh, yeah, that's good. And closing. Overwhelmingly B. You're right. It's instantaneous. That means right at that moment, at that instant, it tells you your speed. It doesn't tell you your velocity because they can't tell you which direction you're heading. And it's not an acceleration. That's a change in speed, velocity. More change in velocity. So yeah, it's just telling you, oh, right at this moment I'm going 56 miles an hour. That's your instantaneous speed. Not an average. All right. How about this one? Let's open it up and see if you can actually do a little math with this. No, you don't actually need an equation. You can use one, but you can just reason this one through. We'll do it if you don't. So you can envision it. You're going 100 yards. Takes you 20 seconds. So what's your average speed? So you covered 100 yards and it took you 20 seconds. We almost have as many votes as last time. A few more seconds, your last few people, get them in. Give her a go. This is great because I get to see if you're all getting it or not. Well, there's one more out there I know at least. Going once, going twice. Sold! All right. Whoa, overwhelmingly B, 96%. You're right. Good. So see, I can tell that makes sense to most of you. And that's average. That doesn't tell you were going 5 yards a second at any given moment. You could have been, but on average throughout it. If you went 5 yards per second the whole time, it would have worked. But in theory, sometimes you were slower, sometimes you were faster. So on average. Did I see a hand? Oh, that was just taking your coat off. All right. Let's do, nope. Nope. That one. Pole. Go. If you were paying attention, I just answered this one. See, this is a good day. You guys are getting lots of participation points. And if you don't realize it, you're getting a clue of questions that might be on homeworks or the test. So, oh, everybody's in? Woohoo! 98% for D. You are right. I don't think we need to dwell on that one then. No. Okay, how about this one? Can you do distance? Go. You guys have been doing this all your life. You just didn't realize it. And it's simple physics. Using speed and time. Figure out your new position, how fast you're going, things like that. Going once. Going twice. Oh, the person's made it in. D is the correct answer. And that's what 98% of you voted. So you obviously get that one. How about this one? Not a number this time. Ball increases in speed by the same amount each second. What's that tell you about the acceleration? So it's not only making me feel good, but I hope it's making you feel good too that you're getting most of these right. So, going once, going twice. Oh, you got them in. Okay, 71% C, 22A. C and A are the big ones. The answer is C. This one is acceleration is a change in velocity. It's a delta V over T, you know, the relationship. A change in velocity, and it takes a certain amount of time. If you make the same change every unit of time, say 10 meters per second every second, 10 meters per second every second, then you're going to be going faster by 10 meters per second every second. So if a ball is increasing its speed by the same amount, 10 meters per second, 10 meters per second, 10 meters per second, it's the same rate of change. A rate of change in velocity is acceleration. So the acceleration is constant. It's some non-zero value, but it's not. The acceleration isn't changing. It's allowing the velocity to change at a constant rate. Does that make sense? If it doesn't, please don't be embarrassed. This is the time. Okay. I think there was another one on here I wanted. No. 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 Doo-doo-doo. Thought there was. See if you got that last one. Answer this one. It's similar. Here's your clue. I'm hoping these are making some connections. Because I know talking about it's one thing, but then, you know, how do I grade you? I got to ask you questions. So I'll see if you can put it together. That's why I put a slew of these together. About 10 more seconds. Go. Well, the last couple get in. It's falling. It gains 10 meters per second each second. What's that tell you about the acceleration? It's constant, yeah, so it's not changing. So it's going 10 meters per second every second. So most of you thought B, half, and the next biggest was A. So we got it between B and A. The answer is B, because it says it's 10 meters per second squared. That's 10 meters per second per second. That's the units for acceleration. A is a velocity, 10 meters per second. The only time it was doing that was after the first second. After 1 second, it had changed its velocity by 10 meters per second. Now it's up to 10 meters per second. But during the next second, it's going to start going faster. And after 2 seconds, how fast will it be going? 20. 3 seconds? 30 meters per second, yeah. So the acceleration is 10 meters per second, or 10 meters per second squared. Yes?
Why would that be steadily increasing?
The velocity is steadily increasing because the acceleration is constant. Acceleration is a rate of change of velocity, and the velocity is increasing steadily, 10 every time. Does that make sense? That's fair. Yeah, this is to help reinforce, because you got position, you got velocity, and you got acceleration. We're used to in normal motion. Well, now we have to specify physics. I'm changing my position. If I'm changing my position, a rate, there must be a rate to that. How fast am I changing my position? My speed tells me that, velocity with direction. But the velocity can be constant if I'm changing it at a steady rate. Well, if my velocity increases, then it must be changing at some rate. We call that acceleration. It's the rate of change of velocity. And if acceleration is constant, then the velocity must be steadily increasing. Yes, you can have the acceleration changing as well. We're not going to go there in this class. And it's actually called, the rate of change of acceleration is actually called jerk. I've never used it in my entire life, but that's what it is. And I just learned last week what the rate of change of jerk is jounce, or they call it snap, and the rate of change of that is crackle, and the rate of change of that is pop. I'm making this up, but we'll stop at acceleration. If acceleration is changing, then sure, the velocity is changing too, but at not some steady rate. It must be some exponential curvy thing. Does that help? And I'm just, we're used to saying increasing. It can decrease too, whether it's positive or negative. Okay, enough of those. I hope that helped. So, lest you haven't put them together, you just used a lot of these. Velocity is the change in position with time. That's some distance you covered in time. And velocity is a vector, it has a direction. Speed's the same thing without direction. Those of you that feeling rusty on your algebra, if you multiply both sides by t, because that's fair, it keeps the equality the same, t on both sides, then you get a t with the v, and the t's cancel on this side because one will be on the top and one's on the bottom, and that just leaves the distance. This is what I grew up with. Distance equals rate times time. Distance equals rate times time. The rate of what? The rate that you're changing your distance. So if they're asking for distance, or they're asking for velocity, or they're asking for time, you can use this equation just by rearranging it, or plugging in the two you do know and finding the third. Acceleration then is a change in velocity over time. And if, say, you want to, you can think of it that way by just rearranging some of the variables. If you want to know how fast something's moving after it's accelerated for a certain amount of time, that's the one I would like. I hope you don't realize these are 4 different equations. This is just 2. You can just rearrange them however you want to meet your needs. You want to know how much you've changed? Well, that depends on how long you've accelerated. Hope that makes sense. This one in your book, sometimes it was written like this at one point, implying the v is a change in velocity. And so I'm going to put it back in there to emphasize that. And the reason they put g in is because g is an acceleration. It's due to gravity. We're used to that one. You let go of something and it accelerates downward. So if you want to know how fast something's moving after a certain amount of time, we can do that. That's great. I'm going to spit off the Golden Gate Bridge, and I time it, and I don't know, for argument's sake, it takes 10 seconds. Now let's make it 5 seconds. What velocity would it be up to? 50 meters per second. What's g? 10 meters per second squared, meters per second per second. That's gravity, rounding up. Technically it's 9.8, but whatever. Don't worry, I'll tell you if you need to use 9.8 or not. I like using 10. It's easier, because this is conceptual. And if it falls for 5 seconds, then after 5 seconds, it'll be going 50 meters per second down. So you know how fast something's going if you knew its acceleration. And Chapter 3 ended with this equation. You can figure out how far you've gone after you've accelerated a certain amount of time. This one's specifically for free fall, but you can use this with an A right there. Any A. Do you want to know how far something's gone after it's accelerated a certain amount of time? They did this. Those of you that were here last lecture, we did the fan cart, and we saw that it accelerated. And I just chose not to bore you. If we plotted the data against time squared instead of, I went 1001, 1002, 1003. If I squared those and then plotted the data, it's proportional. It's a steady rate. And that is directly proportional to distance. This is how Galileo figured this out. We're not going to derive this. We don't need to. He figured out that this works. It observes the motion. And so that's what you can do. So let's go back to this one. You drop something, and 5 seconds later, we know how fast it's going, 50 meters per second. We can now figure out how far it's gone, too. Can you calculate that one? You dropped it, 5 seconds later, how far down has it gone? 1/2 times 10. Gravity, acceleration due to gravity, 5 squared. 5 squared is 25. Half of 10 is 5. I'm trying to make my math easier here. So I can do it in my 5 times.
250 times 1/2.
You can do that too. It's the same answer. Well, take your pick. Or you punch it in your calculator because you don't want to think. That's true. He was saying, well, 25 times 10 is 250, and I can half that, and that's 125. See, it gives you the same answer. That's the beauty of math. It's not subjective. So 125 meters is how far it's gone. See, I've used this a lot. Actually, I was on the Golden Gate Bridge. That's why I used this one. And my sister-in-law decided to, disobey the rule that says don't throw anything off. So she spit her gum out. And we counted how long it took. And I could estimate, to her chagrin, how high up we were. It's kind of fun. I had a well in my backyard. I remember as a kid, I dropped something and I listened. 1001, 1002, 1003. Bloop. Oh, it took 3 seconds to get down there. Well, I knew how fast it was accelerating. So I knew how deep my well was. Physics can come in handy, even if it's just for fun. Does that make sense? And those equations are in your book, of course. So I want to drop something free falling. This, everybody should see this once in their lifetime. Going to lead up to this one. And it's, we've already touched on it. If you drop 2 things, who hits the ground first? You're right. How about a tennis ball and a ping pong ball? Look like the same time to me. If I get up higher, watch them hit the floor. Still kind of looks like the same time. How about styrofoam ball? And not as much murmuring now. Or you're all just looking at me, duh, we know which one's going to hit. Okay, well, here you go. See if you're right. Which one hit first? Yeah, the tennis ball. And you guys know why now. Air resistance. So what forces are acting on both balls? There's 2 forces on each one. Gravity down, air resistance up. For the styrofoam ball, it's affecting it more. And so whose acceleration is greater? Tennis ball. If you count air resistance in, then the acceleration is no longer 10 meters per second. It's a little less because some force is countering it. Does that make sense? So a fun way to do it, okay, we won't clicker question, but I'm going to drop these. You know what's going to happen. Can I drop these 2 so that they hit the ground at the same time? Crunch up the paper? Well, here's, I already crunched this one up, so you really think they'll hit at the same time?
Or at least closer than that.
All right. They do. Or at least with that amount of fall. Yeah. That's the simplest way to do it. So you can bet your friends or something. No, it's not any special paper or something. You know what happens. But then you can really confuse them. You can put it on top. Yeah. There's no air drag on the paper because the book's in the way. So it doesn't get any more air drag than the book does. This one might make more sense because the book pushes it down. But anyway, I want to show you it really does work. Really does work. So I have a feather and a ball. Power on. These are a little electromagnet. I'm going to put the ball on one side, flap while it's held up. The feather on the other side. And we don't have to go to the moon. I'll get rid of the air right now. Close it off. Start pumping air out. and I stall while it pumps air out. You can YouTube video this, the falcon feather and the hammer. The astronaut dropped that on the moon, and they have a video of it. You can see what happens when you get rid of air, because the moon doesn't have an atmosphere. The acceleration on the moon is less than here, so they do not pick up speed as fast. But that doesn't matter, they still fall. We're going to do it here. We're almost there. I'll count to 3, and you guys can follow them down or just watch the bottom half and see if physics really is true or if I'm pulling your leg. But yeah, I would say it's a very, very small percentage of the population that have actually seen this. I bet all of you have read about this, and you knew that, hey, if you do that in a vacuum or without air, they ought to hit the ground at the same time. Well, now's your chance. Okay, that's enough. 1, 2, 3. Woo! See, physics is true. There wasn't any air resistance on the feather, and so it's just the force of gravity pulling it down, and there was no second force to counter it. They both fell at 10 meters per second per second. It works. This is my favorite part, though. It just sounds cool. Boom. All right. So there you go. You got some, hopefully got some dinner conversation. Say, I saw. Or not. Okay. We talked about it last time. When things get enough air resistance, when the air resistance, the force of air resistance up matches the force of gravity down, we call that what? It's in equilibrium, which means no net force, 0. And how is describe the motion of the thing? Not what? Okay, I heard more right answers than wrong. It's not accelerating. It's still moving. It has motion. That's where the motion in quotes you got to specify. It has speed, it has velocity, but it's not changing because it's in equilibrium. And we do call that terminal velocity. A coffee filter shows that well. I know this reaches terminal velocity before it hits the ground. So it accelerates down and about, and you can tell that most of the time it's not getting any faster until it kind of sways on itself. If you make it heavier, here's 4 of them. What do you expect the terminal velocity to be, faster or slower? Faster, because it has to counter more weight. So it still reaches terminal velocity, you can see, but it fell more quickly because its acceleration was its terminal speed, velocity, was higher than the first case. Very good. You guys are getting this. Friction. I'm going to address friction. Your book says there's 2 types of friction. You guys are familiar with this. Everybody's dealt with it. Static friction and sliding friction. So I just added some extra weight here on this block to make it more conspicuous. This is a spring scale which will show force. I'm going to pull on it, and as I pull and pull and pull and pull, I'm exerting a force on it that way, but it's not moving because of the static friction. Static means it's not moving. Between it. Which way is the static friction acting? Point. I'm pulling to your left. I'm exerting a force, so there must be a force countering that way. Friction's acting in that direction. It's generally always opposite the direction it's trying to move, or is moving. In this case, trying. Now watch this closely. I'm going to pull, pull, pull until I can overcome static friction. This is in newtons, by the way, the unit of force. So, I'm 10 newtons, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, there. And now we're moving. And my point is, static friction is almost always more than sliding friction. Static friction is generally always more, equal or more, than sliding friction. It always seems to hold back more until it starts moving. But once something starts moving, it's easier to keep it moving. So it takes more force to get it to move initially. Once it's moving, I don't have to apply as much force to keep it moving. Ready? Let's do it again. Oh, and it slips free, and I can pull. And I'm trying to pull it at a constant force, but, you know, it jerks around a little. Yeah?
Is that principle of sliding friction being less than static friction because of inertia?
Yes, it is because of inertia. Very good. The book explains that really well, too. Thus, if you haven't figured out that, if you leave lectures and you're still confused, I hope you go read the book. That's why I chose this one, because he explains it really well. For some of you, you're probably sitting there going, yeah, you know, I've known all this. When are we getting to the stuff I don't know? Yeah, well, we're building. We're building. I want to mention, too, because we're later going to get to fluids. Same thing applies in fluids. Air, water, blood, things rubbing up against each other. Internally in the, or on the sides of the container or something, it exerts some friction, and we're going to have a force there that isn't always negligible. But the same thing applies. Mass and weight. We need to differentiate between those a little more, a little better. That's why I like this demo. I'm going to suspend this lead ball, because it has a lot of mass, it's heavy, from this string. I am also going to suspend it from this. It's my safety rope. So if this breaks, this doesn't come crashing down. The thicker rope will catch it. And then I'm going to put in the second one on the bottom. Your book discusses this demo actually. I like it. If I pull down on this string, what should happen? That is correct. Explain that, Kate.
Well, if you're pulling it from the bottom slowly, you're adding weight to the ball, and that causes the top string to break.
That was perfect. Yeah, let's pause there. Yeah, there's tension in here. I think you know because the weight, Earth is pulling this down, trying to make it accelerate. This supporting force is balanced. It's in equilibrium. It's not accelerating. Well, I'm going to add to that downward force by pulling on it. I'm adding to the weight. And if I pull down slowly, sure enough, this can't handle that. The supporting force needed exceeds the strength of the string, and the string broke. That's reinforcing weight. Do it again. This time, as Kate alludes to, I'm going to pull down more quickly. If I just jerk this, ready? Then the bottom string breaks. That's because I'm trying to overcome mass. Remember, it's inertia. Once it's at rest, it's put here, it wants to stay there. This couldn't react fast enough, so to speak. The tension couldn't propagate through the string quickly enough, literally. So when I yank on it, this was just still supporting its weight, which it can do. But I added a force trying to move its inertia, and its inertia kept it in place, and that's what broke. That's the difference between mass and weight. Your mass generally does not change, but your weight can. When you get on a bathroom scale, that tells you your weight, how much Earth is pulling down on you. If you take that bathroom scale to the moon, your weight changes. It's a sixth of your weight there, because the force of gravity on the moon is roughly a sixth as it is here. If you go up into an airplane or a really tall mountain, Actually, you're a little farther away from Earth and your weight is actually a little less because it's pulling on you slightly less. But in all three cases, as long as you didn't have Thanksgiving feast in between, your mass stayed the same, even on the moon. Even in space, when you feel like you're just floating around, your mass wouldn't change. So how would you weigh somebody out in space? You can't just plop them on a bathroom scale. You have any ideas how you could weigh somebody in space? They displace? Stick them in water and see what they displace. That would tell you your volume, how much space you take up. Good, but not necessarily how dense you are unless your mass. Any other ideas?
Can you pull them against have a scale mounted and have that the same amount of gravity string pulling them towards that?
Yeah, something like that would work. Good. You raised your hand? Oh, beautiful. Say it again louder.
So you push them in one direction and then see how hard it will be to change the direction.
Yeah, push them one way and see how hard it is to change their direction. Let me plop it up here so you have it for the weekend. And we'll do more on it next lecture. Acceleration. Don't think of it as an equation right now. This is a relationship we're going to go into more depth with next lecture. You can figure out its mass. Think of this mass as inertia, not weight. When you're talking about acceleration. So you need a force. You guys know this. And the book, again, does a beautiful job. This is what I'll reiterate. Acceleration is directly proportional to force. If you push on something harder, you know this, it's going to go faster. You can make it accelerate. You increase the force, you increase the acceleration. Does that make sense to you? Seem natural? Good. That's what we all observe, so that's why Newton came up with his second law. This sums up his second law. You don't have to write out a paragraph. This is it. We also learned that if something has more inertia, for the same force, but it's bigger, it's not going to go as fast. That should make sense to you. This idea. If I try to push on this the same, it accelerates. You know? If I use the same force, it doesn't accelerate as quickly as if same force on one. That's because, well, we observed this. So acceleration is inversely proportional to inertia. Mass is a measure of inertia. So more force goes faster, but if it's bigger, it goes slower. That's Newton's second law, the gist of chapter 4, and that's how you can figure out some guy's mass in space. Like you guys said, instead of trying to just set it on a scale and weigh it, try to just, do this, and you could get quantitative with that by measuring the forces that takes. The more mass something has, the more force I need to change its motion, as opposed to doing a tennis ball. Oh, that's easy. So I already have a feel for its inertia and its mass, how much mass it has. And you can do that with measurements and get numbers.
So if an object's acceleration is higher, you need less force to move it?
Repeat that.
So if an object is accelerating quickly, you need less force to change that path?
What I was saying was to get something to accelerate at a higher rate, you need more force for the same object. You're saying once it's already moving? If you're going to try to change its motion and thus accelerate it, the rate of that acceleration is going to be directly proportional to the force. So if you change it faster, you need more force. It takes more force, and vice versa. If something has more inertia, because it has more mass, that's a property of it, then for that same force, pushing something bigger, you won't have as big a change. And mathematically, this is how you write it. And if you don't see that, plug in some numbers. Say the mass is 10 kilograms, put in 100 kilograms, keep the rest the same, and you'll see that number, which way, direction it changes. Other questions? So my point is, you don't have to weigh it. You can go like this. And in space, what they really do, at least right now, they put them in a chair that's on springs. It's like there's two metal bars here that are springy. They sit in it, and you can kind of swing back and forth, rock back and forth. And they measure the period, how fast it goes back and forth. And they use simple harmonic motion, something we haven't got to yet. But it's all dependent on their mass, their inertia. Not their weight, but their mass, their inertia. The more inertia they have, the slower they vibrate. And the less inertia they have, the less they resist that change, and the faster they vibrate. So hopefully that'll help you keep difference between mass and weight. They are totally different things. I know you want to go, so one more statement. One more statement. It'll help you with homework. Rearrange that, and you have that. If you plug in the acceleration due to gravity, then A is 10 meters per second squared, and that force is the weight. That's how much you weigh. If you take my mass and try to accelerate it downward at the rate of gravity, that's what I call weight. That's weight. Weight is a force. Mass is not. I'm done.